How are you, Sandeep?
So dark.
Okay, I think 4 people have joined apart from me and Sandeep. Of course, NPTEL office on Realme. Who is Realme?
Hello, sir. Good morning.
Good morning, Sandeep.
How are you,
I
sir?
am not able to hear you.
Okay.
Who is this Realme RMX 3241? I don't know who is he.
Maybe someone joined.
Okay, we can ask whether he has any clarification, any doubts. So, how are you, Sandeep?
I'm good, sir.
How are things going on?
Just going on, sir.
Very good.
So I gave that video to one person.
Mhm.
He told I will check and let you know what can be done best.
Okay, that's good.
But
If
still
that is
waiting for
possible,
his.
then I have other things also.
Okay. So he didn't tell me anything. I will call him today again.
Okay, fine.
Huh.
I think they have done a bad job. They have not recorded properly.
Yeah, they have not recorded properly.
Yeah.
Hmm.
So about that hydrogen bonding manuscript, you have started
Which one, sir?
hydrogen bonding for the annual reports.
Okay, that yeah, review. Annual
Mm.
that I have started. I have done something.
Okay.
So I'll show you.
Okay. Good.
So our deadline is July.
Correct. We have plenty of time.
Huh.
There is one person by name Sanchita Tripathi.
Yes.
Hello, madam. Do you have any doubts, clarification, any questions to ask?
Yes, sir.
Yeah. Please ask.
Sir, can I speak in broken English because my English is not so good?
If you can speak in Hindi, Sandeep will understand.
You can
Okay,
speak
sir.
in Hindi also.
You are from which
सर
place?
आपका जो लेक्चर नंबर
हाँ.
रतलाम मध्य प्रदेश.
Hello.
हाँ,
कहाँ से आप हो? हेलो.
प्रदेश. हेलो.
हाँ, आप कहाँ से हो?
सर रतलाम मध्य प्रदेश से.
अच्छा, मध्य प्रदेश से.
Okay.
Okay, so
You can speak in Hindi. Sandeep will understand.
Hindi will okay.
ओके सर, आई हैव अ क्वेश्चन दैट लेक्चर 8 में आपने बताया था कि जो CH2D2 मॉलिक्यूल है उसके कार्बन 13 स्पेक्ट्रम में जो स्प्लिटिंग है कार्बन 13 की सिग्नल की, उसमें स्प्लिटिंग पहले हाइड्रोजन से की गई है, फिर ड्यूटेरियम से की गई है. तो ऐसा क्या किस फैक्टर से डिसाइड हो रहा है कि पहले हाइड्रोजन से होगी फिर ड्यूटेरियम से होगी स्प्लिटिंग?
नहीं, फैक्टर कुछ नहीं है. सी यू कैन गो टू आइदर वे. Okay, first go couple with the deuterium, then you calculate coupling with the hydrogen. There will be no change in the spectrum. The best way is first you consider the big couplings, like which one big. First you consider that, then small like parallel calculations. But either way you calculate, it will be the same. It is not going to change. It is
But
not
sir
like
ने
that it's coupled with any. It just to tell something, sir told, but it is not like कि आप किसी से भी करो कपल. पहले के मतलब एट अ टाइम इट इज हैपनिंग. इट्स नॉट लाइक दैट कि एक से कपल किया फिर दूसरे से कपल किया. इट इज देयर. और एक साथ ही डिटेक्ट होता है, उधर कुछ भी ऐसा प्रायोरिटी नहीं है। बट फॉर अंडरस्टैंडिंग कि पहले बिग कपलिंग्स देन स्मॉल कपलिंग्स।
In fact, in one of the coupling pattern to generate multiplicity pattern, I have shown it. When we have coupled to CH2 and CH3 together to a CH proton, which one should be taken first? Whether we take CH3 or CH coupling or vice versa. I have worked out and shown you the pattern. Pattern remains same. It doesn't change at all. I don't know whether you have seen that slide. If there is a, wait a minute, I'll go to that slide. I'll open that and show you. 1 second.
ओके सर।
Yeah.
बट रिजल्ट चेंज नहीं होगा कुछ
The
भी,
result will not change.
इट विल बी सेम, बिकॉज कपलिंग में कोई प्रायोरिटी नहीं है, मॉलिक्यूल इज इट इज हैविंग कपलिंग्स, यू डिटेक्टिंग।
बट सर हम कुछ और करना चाहते हैं।
हाँ बोलो ना।
तो सर अगर उसमें चेंज नहीं होगा, लेकिन जैसे पैटर्न रहता है ना कि ट्रिपलेट ट्रिपलेट बाय क्विंटेट ऐसा रहता है, और फिर क्विंटेट फ्रॉम ट्रिपलेट, तो ये जो
हाँ,
सीक्वेंस,
that name should be by the first big coupling should be considered, then small couplings by giving the names.
See what will happen at that time. Let us say you have a triplet and a doublet. Consider an example. If coupling of triplet is larger, let us say 20 hertz, then each layer of the triplet can be split by into a doublet with coupling small, let's say 5 hertz. Which is the largest coupling? Triplet. Is it not? So you have to consider that as the first and then doublet as the second. It is called triplet of doublets. Alternately, if doublet coupling is 20, triplet coupling is, let's say, 5 hertz, then you call it as doublet of triplets. You understood? Sandeep, you tell her in Hindi.
हाँ, see,
आई
अगर
अंडरस्टैंड इंग्लिश।
understood, she understood.
You understood. Very good. Very good.
So
You understood?
that is the, अगर आपको बोलना है कि क्या कपलिंग पैटर्न है, तो बड़ा वाला कपलिंग फर्स्ट भी कंसीडर, देन स्मॉल वाला। अगर अदरवाइज बाय ड्राइंग सपोज तुमको कुछ बोला गया कि कपलिंग पैटर्न कैसा आएगा, देन देयर इज नथिंग टू बी फॉलो द रूल, लाइक इट विल बी सेम, पैटर्न वैसा ही आएगा, चाहे किधर से भी प्लॉट करो, मतलब किसको भी पहले कंसीडर करो।
It
सिर्फ
doesn't
नेम में
matter.
चेंज,
हाँ
मतलब पैटर्न तो सेम आएगा हम दोनों तरफ से अगर
हाँ
करें।
हाँ, बस नाम लिखना है अगर कि क्या है, ये ट्रिपलेट ऑफ डबलेट है या डबलेट ऑफ ट्रिपलेट है। तो जो बड़ा कपलिंग है फर्स्ट, सपोज से कि CH3 के साथ कपलिंग, CH के साथ कपलिंग बड़ा है, ठीक, 20 हर्ट्ज, फिर वो फर्दर कपल कर रहा है CH2 के साथ, तो उसका सपोज से 10 हर्ट्ज। सो फर्स्ट you say 20 hertz, then in 20 hertz 10 hertz it will split into again, so that is why you have to say accordingly with the big.
ओके सर, तो अगर हम इसी चीज को, जो एग्जांपल था CD2 CH2D2 था, तो
हाँ,
इसमें अगर हम करना चाहेंगे इसके पैटर्न को, तो हम उसे ट्रिपलेट ऑफ क्विंटेट कहेंगे कि क्विंटेट ऑफ ट्रिपलेट कहें वहां पर?
See, in
ओ,
the, she is asking in CH to D2, CH to D2, Sandeep.
हाँ हाँ
CH2, CH coupling is quite large, about of the order of 150 or 200 hertz.
हाँ हाँ,
Whereas CD coupling is very small.
ओके,
You understand?
हाँ हाँ,
As a consequence, if you are looking at carbon 13, you have to say triplet is large, big coupling is triplet. And then coupling with deuterium is very small. And it is a D2, the deuteriums, which gives rise to a quintet.
then triplet of
couplings,
quintets.
yeah, it is triplet of quintets. Each line of the triplet is going to be quintet. You understood? Sarita
Yes,
ji,
sir.
मालूम हो गया?
यस सर।
Then coupling, biggest coupling is triplet. It is called triplet. And then each line of the triplet is split into two deuteriums. It is a quintet. So you call this pattern as triplet of quintets.
ओके सर, यस सर। और सर एक और था जो हमने आपको एक और सेंड किया था कि जो फैक्टर है कपलिंग कांस्टेंट के लिए, जैसे आपने बताया था कि एक 10 बोरॉन हाइड्रोजन का जो कपलिंग कांस्टेंट था वो 26.7 हर्ट्ज था, और वही 11 बोरॉन हाइड्रोजन बॉन्ड का जो कपलिंग कांस्टेंट था, एक मिनट राइट डाउन किया है, वो 64.9 हर्ट्ज था। तो यहाँ पे ऐसा क्या चीज है जिसके कारण सिर्फ एक इलेक्ट्रॉन चेंज होने पर, सॉरी न्यूट्रॉन चेंज होने पर इनकी कपलिंग कांस्टेंट में इतना ज्यादा वेरी हो गया?
Okay, now I'm completely lost. Sandeep will answer this.
Okay, can you repeat?
Yeah, he will answer you in Hindi.
Repeat once.
सर, जो सर ने एक एग्जांपल हेटेरोन्यूक्लियर कपलिंग कांस्टेंट में एक्सप्लेन
हाँ,
किया
हाँ, हाँ,
था। हाँ, तो सर उसमें उन्होंने बताया था कि 10 बोरॉन हाइड्रोजन
हाँ।
का कपलिंग कांस्टेंट है वो 27.3 हर्ट्ज था।
How much?
सेम कंपाउंड 27.3 हर्ट्ज।
10 to 7 means
27.
27.
Ah,
हाँ,
Okay.
27.3 हर्ट्ज।
हाँ, हाँ,
और वहीं 11 बोरॉन हाइड्रोजन का जो कपलिंग कांस्टेंट था
हाँ,
वो था 64.9 हर्ट्ज।
हाँ।
तो ये इतना डिफरेंस सिर्फ एक न्यूट्रॉन के चेंज होने पर कपलिंग कांस्टेंट इतना ज्यादा वेरी आ रहा है, जबकि
नहीं,
दोनों में
नहीं,
बोरॉन
see,
कपलिंग ही है।
नहीं, नहीं, बोरान सेम नहीं होते हैं। एक्चुअली क्या होता है ना कि न्यूट्रॉन चेंज होने से या उसके अंदर प्रोटॉन चेंज होने से उसकी आई वैल्यू चेंज होती है। ओके।
ओके सर।
सो आई वैल्यू डिसाइड करती है कि उसका क्वाड्रुपोलर इफेक्ट कितना है। सो ड्यू टू दैट क्वाड्रुपोलर इफेक्ट आल्सो देयर इज सम ब्रॉडनिंग। तो वो ब्रॉडनिंग की वजह से कपलिंग एक तो मेजर नहीं कर सकते, उसके लिए वो कम दिखती है। दूसरा चीज ये है कि कपलिंग कंप्लीटली डिपेंड्स ऑन द ऑर्बिटल ओवरलैप एंड ट्रांसफर ऑफ मैग्नेटाइजेशन और दिस देन वो किसमें ज्यादा है किसमें कम है, वी कैन नॉट डिसाइड दैट। दैट इज इंट्रिंसिक प्रॉपर्टी। That depends on angle, depends on overlapping, molecular overlapping. Accordingly, we get that coupling.
ये सर, ये तो मतलब कि स्पेक्ट्रा जब देखेंगे तो
हाँ,
हमें ये सब कैसे पता चला कि जो 11 बोरॉन हाइड्रोजन का जो कपलिंग है
हाँ,
और बोरॉन हाइड्रोजन का जो कपलिंग में इतना ज्यादा डिफरेंस दिख रहा है?
so it can be. The couplings can be different. Not only boron 11 and proton or boron 10 and proton. In the same molecule, for example, you take carbon 13 spectrum. One carbon with proton coupling can be 200 hertz. Other carbon within the same molecule can be
that
150
can be
hertz.
less than 100 hertz.
Can be different. It depends upon the charge distribution at the site of the nucleus, how the polarization transfer to coupled spin, how the bonds are,
How it is
orbitals are
overlap? How
overlap.
orbitals are overlapping?
That is the important
At
thing.
what angle they are overlapping?
So
What is
geometry matters.
their hybridization? All those things
Correct.
contribute to the J.
Correct.
बट सर BH4 मॉलिक्यूल में कैसे डिसाइड हो रहा है? उसमें तो सारे एंगल सेम है,
नहीं,
109.25
बट ऑर्बिटल ओवरलैपिंग और उसका जो मैंने बोला क्वाड्रुपोलर इंटरेक्शन से भी उसका ब्रॉडनिंग इफेक्ट से जे कपलिंग कम या ज्यादा हो जाती है, कि मतलब तुम मेजर नहीं कर सकते डायरेक्ट।
मीन्स ये वैल्यू जो आई एक्सपेरिमेंटल, हम इसे किसी फैक्टर से ऐसा नहीं बता सकते यहाँ पर।
फैक्टर से है कार प्लस इक्वेशन, बट नॉट फॉर दिस यू कैन नॉट, बिकॉज देयर बॉन्डिंग इज ऑलमोस्ट सेम। लेकिन वो कार्बन बोरान 11 का
One has spin 3/2, other is spin 1. The quadrupolar coupling, that means charge distribution at the site of the nucleus, both of them are quadrupolar, the extent of charge distribution is different. It is not same. As a consequence, quadrupolar coupling or quadrupolar interaction will be different. All these internal, the geometry, this matters a lot. Charge distribution matters a lot.
See, for spin 1 you have 3 energy levels. For spin 3/2 you have 4 energy levels. So accordingly their transitions and also the J value also depends on the energy separation. That is only J, the energy separation only with the additional energy levels which generated due to the coupling. So in 3/2 it will be different and 1 it will be different, because there you have only 3 energy levels. 1, 0, -1, and here you have 3/2, 1/2, then 0, minus, not 0, -1/2 and -3/2. So accordingly, when the energy levels will arrange themselves due to the coupling, so it will be different by in case of 1 or in case of 3/2, because gamma is different, V naught is same, everything is. The many things affect actually. That is you have to go to deep to the quantum mechanics to understand in which it will come more, in which it will come less, and why it is coming.
Okay. Okay.
So
Thank you, sir.
there are many factors. It is not one actually. There is only the orbital overlap. Orbital overlap, not orbital overlap. Sorry, dihedral angle. That will only will be mattering when you have the same fixed. Like carbon is same 13C, proton is same 1H, proton is 1H. Then if you are considering which one will be more, then depends on the according to the Karplus equation on the dihedral angle. But if it is nucleus is isotope is entirely different, then many things come to the picture which are there common, so we don't consider them. But here you have to consider. You have to consider their energy levels, orbital splitting, overlapping, many things. Then you will get which one will give a big coupling or a small couplings.
Understood?
Okay, sir.
Part two isotopes you cannot consider, okay? Because you cannot compare two different isotopes on one factor. On one factor.
I'll tell Sanchit in a simple way. CH coupling you consider. Carbon and proton. You understand? Carbon and proton. See what will happen? The nuclear spin of, let us say, hydrogen, it will in turn align its electron. This electron through covalent bond make sure that other electron of the carbon gets aligned. Whether it is parallel or anti-parallel, that's a different question. And that orientation again affects the nucleus of the carbon. Through this mechanism, there is a transfer of polarization between one nuclear spin to other nuclear spin mediated through covalent bond. Similarly, this is for two spin-off nuclei. If you consider spin 3/2 and spin 1 nuclei, their charge distributions will be a different pattern. It is not a dipole. You can't simply take a circle and then do it. Where are you? She's disappeared.
No, she's muted, but
okay. So, see, it is not a fairly simple mechanism to explain when you have a quadrupolar spin like this for two different isotopes of the same nucleus. You have to go deeper into understanding of quantum mechanics.
You have to understand the spin dynamics, quantum mechanics of this. Then you can calculate for a particular isotope. But if you are comparing, then what is the effect? So, dihedral angle generally matters, but for same, if you everything is same, like same isotopes, same nucleus, then you can say why it is different than angle. Otherwise, many factors that contribute to the couplings and other interactions also.
See, there is one question from in the chat box. P. John C. Lakshmi student. I need NMR spectrum of molecules. I mean, how to spectrum developed. I see. I don't know what is she asked. John C. Lakshmi, are you still there? Can you please come online? I'm not understanding what you want.
No. This is someone, see, Jhansi Lakshmi student, like this is from the college, that is Jhansi Lakshmi, I think, maybe.
Correct. She wants to know, I need NMR spectrum of molecules. I mean, how to spectrum developed. She is possibly asking how to record a spectrum.
See, you have to have an NMR spectrometer. Otherwise, you have to contact someone who has the spectrometer. We can write.
Okay.
Hello.
So you for this you can contact Sandeep. He will explain to you over phone or email.
Someone is talking. Hello.
Dr. Sandeep Kuldeep Singh Rathore.
Yeah.
Hello. I am asking, what is the difference between spin lattice relaxation and spin relaxation? It is the same phenomena in polarization transfer, or is it different? Okay.
No, They are completely both are different phenomena.
Completely different phenomena.
Shall I explain, or Sandeep, you would like to do that?
No, you can explain, sir.
Little bit, sir, explain.
Okay. I'm sorry, I didn't get your name. What is your name? Kuldeep. Dr. Kuldeep
Kuldeep.
ji. See, what is going to happen is, first we are going to, there are two ways to understand spin lattice relaxation. I'm going to tell you in a first simplest possible way, and then come to the more detailed explanation later. You take this sample in NMR tube, okay, and then put it in a magnetic field. Simplest experiment I'm doing. And I will not wait even for microsecond. As soon as you put the sample in a magnetic field, I am going to send a radio frequency pulse and collect the signal. I will not get any signal immediately. You know why? The reason is, it takes some time for the nuclear spins to orient themselves in a magnetic field. You understand? To develop what is called population difference. And the time which requires for the spins to attain thermal equilibrium, this population difference will be developed after certain time called, to attain thermal equilibrium, called the relaxation time. That is the time for the nuclear spin to attain thermal equilibrium. Then if you apply a radio frequency pulse, you are going to get the signal. Forget it. It's a simple way. Now I will tell you what is T1 in a different way. Now I have put the sample in a magnetic field.
Yes.
I apply radio frequency pulse. What is going to happen? Remember in the NMR tube, there are a lot of molecules. So many molecules are there, and I consider nuclear. We talk in terms of nuclear magnetic moments, or in other words, each nuclear spin I can consider like a small dipole, nuclear magnetic moment. As soon as I apply 90-degree pulse and bring it to x-axis or y-axis, instantaneously, that means there is what is called a phase coherence. What do you mean by phase coherence? All the nuclear magnetic moments will be perfectly aligned along x-axis or y-axis, whatever it is, where you are going to bring the magnetization or the nuclear moments. Where are you going to bring it? And in that axis, instantaneously, they are all aligned. That is called, they are in phase coherence. But what is going to happen is, slowly with time, this phase coherence is going to be lost. Why it is going to be lost? Again, it is a different theory. Okay, I have explained to you in one of the classes there. Maybe in this class or in the previous class. No, not in this previous course. Because of the dipolar field that is going to be generated due to various phenomena in the molecules. Could be dipolar, but could be perturbation of the molecule, rotation, and various things can happen. And each of them will happen at particular frequencies in time. You take this, interactions are their molecular oscillations, perturbations, rotation, whatever it is, collect as a function of time and do the Fourier transformation. You are going to get some frequencies. These frequencies match with this, the dipolar interaction, whatever the frequency what you are going to generate will interact with the nuclear dipole field there at the set of the nucleus. There are too many dipoles are present. There will be an interaction. These two will match. As a consequence, what will happen? Slowly they will start defacing. Don't worry more about details. Simply understand with time, the phase coherence gets distorted.
Okay.
What does it mean?
Thank you, sir.
No, wait. I have not completed. You listen to me completely. Okay, so phase coherence is going to be distorted. What does it mean? The nuclear magnetic moments start, the nuclear spin vectors start moving away from the particular axis where the coherence is going to be lost. And at this, when this keeps from one axis, x-axis, let us say, slowly they will start going like this, completely one circle, it will come back. Then the whole phase of this is going to be lost in the XY plane. The time it takes for the nuclear spins to lose this phase coherence in the XY plane is called T2, or spin relaxation time. I'm giving you only hand-waving argument. In my lectures, you have explained everything in detail. You can go back and listen to it again. But what is happening is, when you bring the magnetization at the, to the x-axis or y-axis, you are disturbing this system. What was in thermal equilibrium, you are disturbing it. Now what will happen? No system in the universe wants to be disturbed. They want to go back to equilibrium. So slowly, the spins start attaining equilibrium. What do you mean by attaining equilibrium? It will develop again population difference, slowly go back and align along z-axis. You are getting the point.
Yes, yes.
Simultaneously, when it is decaying, it is also growing along z-axis.
Just a minute, sir.
Yeah.
Okay.
Tell me.
Sir, the signal we absorb on the spectrum, we see on the spectrum is coming from the rotating frame, XY plane, not in the Z-axis.
Exactly. It is a coherence you are detecting. NMR is what is called a coherence spectroscopy. As soon as you bring the magnetization, there is going to be coherence developed. That's called coherence. And you are collecting the signal as a function of time. And you do the Fourier transformation, you get the NMR spectrum. That is different. Okay. That is nothing to do with T1 and T2. So you understood what I am telling you. T2 is a decay in the of magnetization or defacing in the XY plane. T1 is the growth of magnetization along Z-axis.
Okay.
Both are exponential functions. It follows exponentially. One is a decay function, other is a growth function. And these two times are not same, they are different. Okay. You understood? So relaxation, yes, the growth of magnetization along Z-axis is called T1. Or in other words, spin lattice relaxation. Okay. You understand?
Yes, sir.
The decay in the XY plane is called spin-spin relaxation, or also called T2. Okay. You understood?
Yes.
Okay, fine. See, for the question of how to record the spectrum, Sandeep has already answered in the chat box.
Okay.
Anybody has any other question? Who is that? There is one person by name Will has joined. Will 5. Who is Will J5?
I think Wilson.
Oh, our Wilson. Is it? Okay, okay. So any other person who has any doubts?
Tell me. I would like, the 2D NMR spectrum, the basic difference between 2D and the 1D dimensional spectroscopy, there is a difference in rotating framework or what it is. Means the 2D NMR spectroscopy and 1D NMR spectroscopy.
Okay. Did they already in this course have I come to 2D already or not?
Oh, no, it is a repeat course. 2 lectures I have. Okay, okay. Previously course I did not join.
No. In this course, I don't think I have come to 2D yet, right?
No, you did not complete it yet now.
No. 2D course, in this course itself, 2D I will start maybe after another 1 week or 2 or so. Then I will explain everything. You can see what it is. Remember one thing, 2D means signal is acquired in 2 dimensions. 1D is signal acquired in single dimension. And when the time, you collect the signal in time, you do the Fourier transformation to get the frequency spectrum. In 1D, you do single Fourier transformation. In 2D, you collect the signal in 2 dimensions and you do the Fourier transformation in both the dimensions. How we acquire signal, how we do this experiment, what is the difference between 1D and 2D, everything I explained for almost 3 classes. When I come to 2D, you will understand that.
Okay.
In this course itself. Otherwise also, remember another course is going on parallelly in January session. There I have extensively discussed more about 2D and 2D spectral analysis. You can see there also.
Okay.
Anybody else? Sanchita, you are finished? You have any other problems?
No, sir.
No, you can take advantage of this time and ask questions if you have not understood in the class. This is the time you can interact. Don't worry, even if it's simple question, you can ask. If you know, we will tell you. Otherwise, we'll come back and tell you in the next class. Kuldeep ji, you have any other questions?
I am thinking if the less sensitive nuclei in biological molecules, proteins, there is a very less sensitive nuclei. Natural abundance is very, very low.
I know.
So in that case, and there is number of nuclei is very more in ATP, ADP, such kind of molecules.
Okay.
So how do we get it the exact spectra in that case? We have to increase the frequency, or it is possible in 400
Okay.
500.
Do you answer, Sandeep, or shall I answer?
Yeah. See, if natural abundance is less, sensitivity is less, you have to give for more scans. And you can go to the cryo attached NMR spectrometer. So there, the noise from the electronics can be reduced by multiple times. So signal to noise will be better. So you can get spectrum.
Sandeep ji, for protein molecules, we are generally taking 700 megahertz. Why not 500, 400? Can you tell me?
See, generally, yeah, that is all sensitivity also matters by root root of 3/2. Sensitivity if you go to the one spectrometer to another one. Okay. And other one, the second thing is mostly the higher frequency spectrometers are attached with the cryo probe. But have you seen anywhere 400 megahertz spectrometer is attached?
400 I have seen in my institute, but 800, 700.
No, that is not with cryo probe, right?
Okay.
And other thing is where in protein and all you have many signals. They having the difference in their resonating frequency of few hertz only. So that will overlap in 400, but in higher frequency they can be resolved. So that is also the advantage of doing it at a higher frequency.
Okay. Kuldeep, are you biologist? Are you biologist?
No, sir. No, I am organic synthetic chemist.
Okay, I'll tell you one thing. In the case of proteins and biomolecules, the molecular size will be bigger and the number of protons available in a given molecule will be enormous. And the spread in frequency, chemical shift range for protons is the order of 10 ppm. If you go to 400 megahertz, 10 ppm is 4000 hertz. In that small range, lot of peaks will be there. And they are all overlapped. In addition to chemical shift, couplings will be there. Varieties of the interactions would be there. As a consequence, the spectrum is very, very crowded. It is very difficult for you to analyze. So you go to higher frequency spectrometer. From 400, you go to 700 megahertz. Now, what is the spread? Same 10 ppm becomes 7000. It is like stretching, you're expanding it. So resolution is better. So one thing, for big molecules, you go to high frequency. And for natural abundance, two things you can do. Increase the sample concentration. That is also not possible beyond a certain limit. What will happen? Samples get aggregated or, dimerization. Many important phenomena can take place. And if you make too much concentrated solution, then spectrum will be very broad. There won't be sharp lines because molecule mobility is restricted. That's another problem. And also what will happen is, for a low abundant nuclei, what we can do is we can do isotopic labeling. So that's what most of the biology people will do. You know what is isotopic labeling?
You explained in the lectures.
Okay, we can expand, we can enhance this particular spin. For example, carbon 13, abundance is 1%. I can do isotopic labeling, make it 100%. Then it is as good as saying that it is a 100% abundant spin. So we can enhance the intensity by doing what is called isotopic labeling. That's one more point. So another point is we have an NMR experiment called polarization transfer, which I don't think I have come to this yet in this class, in this course. We can transfer magnetization from abundant spins to rare spins by using some method, which I have already explained in the course. You will see that. Then the less abundant spin will become more abundant. Signal intensity goes up. In other words, it is like telling I'm robbing the rich and paying the poor. I'll tax a rich man, give it to the poor people for the development. Similarly, I can take the proton magnetization, give it to carbon 13 or nitrogen. Then signal intensity goes up. This is another way. There are many possibilities to enhance the signal intensity and to detect nitrogen 15 and carbon, etc. Less abundant spins, even in biomolecules.
Okay, sir.
You got it?
Yes, I got it.
Okay. So any other questions? No, you don't have to worry. If you have any other question, you can send an email. See, Sandeep or myself will answer you.
Sir, I just want to ask once again,
Sure.
the signal noise ratio, intensity
I am not
increase
hearing you.
means
Can you please be loud?
Okay, sir. Sir, the signal noise, if we want to increase the intensity of the signal, so really we are decreasing the noise, signal noise is decreasing, or either signal is intensity while taking the spectra.
Signal.
See, both
Okay,
the
Sandeep.
things are there. Both the things are there. So when
Okay.
we are acquiring spectrum, first suppose you have one scan, then you two
Okay.
scan, 10 scan, 100 scan, 1000 scans. Okay. So every time signal will come with the same rate and noise will also come with the same rate. But noise is random. Okay. Signal
Okay.
is coming at one position only. So it will add up. But noise cannot add up because it is random. Somewhere now it is somewhere, next time it will be more in another place and it will add up, but not in that rate, which rate that spectrum is being added. Your
Okay.
signal. Okay. Because signal having fixed position. So that is one thing. Second thing, noise is coming. If you can reduce the noise, then signal to noise ratio will be more. So then intensity will be high. So that is the due to that is cryocooling.
You understood?
Yes, sir.
You simply remember when you are acquiring the signal, signals from the sample will be always in phase. Whereas noise is random. That's what Sandeep said, noise is random. So phase is not always same. They keep changing the phase every time you acquire. So as a consequence, they add up not coherently. Whereas phase, the signal is always going to add up because they are of the same phase. That's why when you acquire for a long time, the signal keeps on building up, whereas noise slowly getting averaged out. You got the point?
Yes, sir, I got it.
I think this I have explained to you. It's a signal to noise ratio in maybe not in this course, in the previous course. In this course, I'm not touching those much such fundamentals, I think.
Okay, sir. Okay.
You can, if you have any doubts, you see in my previous course where a lot of fundamentals I have discussed, basics.
Okay.
Otherwise, you send an email to Sandeep or me, we will answer.
Okay, sir. Okay.
Any other questions? Yeah, I was Sanjita was asking me, can I share this slide?
Yes, sir.
I'll show you. Okay, Sanchita. Hello,
Yes, sir.
Sanchita. Are you
Yes, sir.
there?
Yes, sir.
Look here. This is where I'm explaining the pattern in which you have, both the pattern you can do. It makes no difference. That's what I told you, Wait. Look at this. I am considering the pattern. a molecule like this, hypothetical molecule. Don't worry about existence of molecule, covalency, and all those things. I am considering the CH proton. Look at this proton, a single proton. It is coupled to CH2 and CH3. What is the pattern you are going to get? Here I am considering the situation. Couplings, this coupling and this coupling both are same. You understand?
Yes, sir.
I am not telling, the one is larger, other is smaller. If this is larger, then you say triplet of quartet. If this is larger, then you have to say quartet of triplets. But here, interestingly, I am making J couplings between CH2 protons and this one. That AY coupling and AS coupling, both are same. I have taken that as my assumption. You got the point? Now I am looking at CH proton. When it couples to CH2, what is the pattern you are going to get? You get a triplet, right? The CH proton, when it is coupled to CH2 protons, you will get a triplet. That's what you are going to see it. Now it is split further with CH3 protons. Each of them is going to be quartet. And because of equal couplings, these central lines will overlap. Some of them. I have written the intensity pattern, everything here. You can see in the lecture, in the video, you will see that. If you take the intensity pattern, it turns out to be 1:5:10:10:5:1. We call this as a sextet. Now what I did, I took this coupling first, and then this coupling to this one. First I took AX by AY coupling, and then I took AS coupling. So we got the pattern sextet. Your question was why we have to take this first or this first. Which one we have to take, you don't know. That's what you asked me in the CH2D2. Now I'll consider what happens if CH3 coupling is considered first. It is a quartet instead of triplet. First I took this, it was a triplet. Now I'm taking this, so it is a quartet. Now it is coupled to CH2 protons of equal strength. What will happen? Each line is going to be a triplet. We calculate the intensity pattern and everything, when it is overlap, again it turns out to be same. 1:5:10, same. What is this? It is again a sextet. There is no difference whether you consider this coupling to this first to work out the multiplicity or this coupling to this. Doesn't matter. So I have written to you. I have explained there in the class, splitting pattern is invariant with the order of the coupling chosen for obtaining multiplicity. That's what Sandeep told you, Whether you take CH2 cup first or CH3 first to work out the multiplicity, it doesn't matter. Finally, the pattern remains same. You understood?
Yes, sir. हेलो.
Yeah, hello.
हाँ, बट सर इसमें जो नेमिंग का है वो तो चेंज हो जाएगा फिर वापस.
Naming depends. First depends on the first you have to consider big coupling, then you have to consider small, then smaller. Like that you have to say by naming. Suppose bigger coupling giving you triplet, so you have to say triplet first. Then triplet of, then it is giving doublets, then triplet of doublets, or triplet of quartets, or triplet of quintets, whatever it is. But first you have to say big coupling by naming.
तो सर ने बताया कि अगर हम पहले ट्रिपलेट से, उन्होंने कहा ट्रिपलेट से फिर सेक्टेट मिला है, तो हम ट्रिपलेट ऑफ सेक्टेट जो उन्होंने दूसरा वाला करके बताया जिसमें क्वार्टेट ऑफ सेक्टेट है वो कहा,
जो अभी करके दिखाया वो.
यस सर.
नहीं, उसमें तो दोनों का पैटर्न सेम ही है, पैटर्न कुछ चेंज ही नहीं हुआ.
Explain what I showed Sandeep in Hindi for her. CH coupled to CH2 और CH3.
इधर तो पैटर्न चेंज ही नहीं हुआ ना.
Couplings both are same.
वो तो सेम पैटर्न रहा ना, वो तो हो गया सेक्सटेट. तो सेक्सटेट है. लेकिन अगर मान लिया एक है कि फर्स्ट सपोज एक प्रोटॉन से तुमको एक टाइप के प्रोटॉन से आ रहा है ट्रिपलेट, ओके, दूसरे प्रोटॉन से आ रहा है क्वार्टेट. सो फर्स्ट यू हैव टू सी विच कपलिंग इज बिग. Either triplet coupling is big or quartet coupling is big. If triplet coupling is big, then it is a triplet of quartets. When it quartet pattern is big, and then it is a quartet of triplets.
But in this example, we have taken both the
There is
couplings
no
are
pattern.
same.
There is no pattern. So only one is splitting.
Only one splitting I am explaining.
This is no naming pattern. This is just separate.
I just
Section.
wanted to show you how to generate multiplicity, which one you have to consider first. This question was asked by somebody. That's why I made this slide to show that whether you take CH2 first or CH3 first, doesn't matter. You take first CH2 and then bring the coupling of CH3, it remains same. Or take CH3 first, bring the coupling of CH2, that also same. There is no difference. So
See,
what
Sanchita.
I
Hello.
wanted to say is the order of coupling which you consider to generate multiplicity is immaterial. It does not matter.
Don't change.
That will not change. You understood?
Yes, sir.
जी
Sir.
मालूम हो गया?
हाँ, यस सर. बट सर अभी आपने जो 2 एग्जांपल्स बताया ना स्लाइड्स में, तो उसमें अगर हम उनका नेमिंग करेंगे तो नेमिंग
तो
करने के
नेमिंग नहीं.
Section है ना, both it is
both are
section
same coupling. Of course, I tell you one thing. In the same thing, if CH3 coupling would have been larger, then we call it as quartet and triplet. If CH3 would have been larger, we call it triplet or quartet. I can generate the pattern again. Doesn't matter. It won't be septet or sextet. It will be different pattern, but still the pattern remains same. Whether you take CH2 first or CH3 first, it doesn't matter. If the couplings are different, you worry about whether it is triplet first or quartet first.
Okay, Sanchita.
You tell her in Hindi, Sandeep.
Hello, Sanchita.
Yes, sir, I understood.
Yeah, actually, see, suppose one proton is there in your molecule. It is coupled with another H. One group is H, another group is CH2, or you can say 2H. Okay, so it is coupled with coupled with H, and also another group is 2H, means CH2. Okay, one is CH, another is CH2. So what will be the coupling pattern? Tell me. Hello?
Doublet of triplet.
Why?
Because
I didn't tell which coupling is big, which is small. So you cannot say like that. So the condition provided, now I say, see that H coupling with CH is larger than the CH2. Then it will be doublet of triplets. Okay. A doublet of triplets, right?
Right, sir.
But if I say that CH2 coupling with this H is bigger than the CH coupling, then it is a triplet of doublets. But
I'll show it to her. Okay. Sanchita.
This is the case you can take.
Yes.
Sanchita, you see this one? I am showing you an example in a molecule like this. This is a molecule. I'm concentrating on proton A. It is coupled to CH2. It will become a triplet. When it is coupled to this single proton, it will become doublet. Now, which coupling is larger? I have taken AX is larger than AY. That means CH2 coupling with proton is larger than this coupling. That means triplet is larger. So I will first write a triplet, and then each line of the triplet will become a doublet because of this. What do you call this pattern? Which is the largest coupling here? What is the largest coupling here? Triplet.
AX.
AX is larger, the triplet coupling is larger. So it is called triplet of doublets. First large coupling you have to take into account. Okay, go further. I'll show you here. Same thing. Now I'll consider AY larger than AX. Doublet is larger. What will happen? Large coupling is doublet. Each of these doublet is going to be a quartet. What do you call this?
Doublet of quartet.
Exactly.
Yes.
Same way. So if
That
on
is
the other
your
hand, if
question.
this simple, you have to consider the largest coupling first and then the smaller coupling. If there are three couplings, what you will do? First largest, second largest, and then the lowest.
Least, lowest.
You got the point?
Yes, sir.
See, for example, this one. Here, I wanted to show you here, it is a doublet of quartet. But the same thing, if this coupling is larger, it is going to be quartet of doublet. See the pattern? Here it is quartet of doublets. In the previous example, it is doublet of quartet. See the pattern? Are you getting the point or not?
Yes, sir, getting.
So this is how you have to understand the multiplicity pattern. First, consider which coupling is larger and name that as the first and then the following ones. If there are many, you have to go in the sequential order. Large, largest, larger, large, like that you have to arrive at the multiplicity pattern. Anybody else? There is one more lab ASC 66 are joined. LBASC 66. Who is that?
Don't know.
I don't know. Hello? Some LBASC. I don't know who is that person. You can unmute and ask questions. All right. Sanchita, I hope it is clear for you. Multiplicity pattern, how to arrive at.
Yes, sir, I understood.
Yeah, if you have any doubts, you send a mail to one of us. We will answer it. In the same platform is there where people post questions, then myself or Sandeep will reply for it.
Yes, thank you, sir.
Any other doubts, questions?
Kuldeep ji, you have any other doubt?
No, sir.
Thank you.
It's okay.
Okay, so you can write us on NPTEL or personally also you can write. So no
You
problem.
can write for Sandeep, you can give your email to them. Sandeep's email is there. He's a brilliant student of mine. You can write to him. He will answer all the questions. He's a well-trained person. Of course, you can also call us but whenever we are free, we can answer you. If you don't want to send email,
Calling
you can call
depends.
us.
Suppose we are not free, then they are calling, so it will be.
That is a different question. So better is send email. We will answer you. Sandeep has posted his email ID. So you can note down or take a photo of the screenshot. It will be useful for you to correspond. All right. If there are no other questions, there are no other people who joined. I think those who have joined also have left already. So should we call it off? 5 more minutes time is there. If you don't have any questions, since there are no other new people who have joined, we can call off. Tell me, Sandeep, Kuldeep, you have anything to ask or should we call off?
Let's call off, sir.
What about Shanticha? You have anything to ask?
No, sir.
Okay. So there are no other people who joined. I think we'll almost time is up. Only 4 minutes are there. We'll end this session. Maybe one more live session would be there. At that time, you can come back with more questions if you have. In the meantime, you can also correspond with us. Okay. Thank you very much for all of you. We'll see in some other time.
Okay. Thank you.
Okay, Sandeep. Wilson.
Thank you, sir.
We'll see tomorrow for Sandeep. Okay.
Yes, sir. Yes.
Thank you then. Bye.